Hello everyone. Suppose you are given an organic compound whose structure is unknown. Your task is to figure out what its molecular structure is. One of the most useful tools to achieve that task is the NMR spectrum of the compound. Now, the most common kind of NMR would be a proton NMR, but also a value is C13 NMR. In this video, I want to focus on the proton NMR spectrum for an unknown and how you use that information to elucidate the structure of the unknown. And there are a number of steps that one follows. Now, as I outline this, the steps may not be always followed in the same order, and we're going to illustrate with some examples. The very first thing you want to do is, assuming that you know the molecular formula for the unknown, is to compute the HDI value for it. Now, in a previous video, I've discussed how one does that. Then the next thing to consider is other spectral information, primarily the IR spectrum, or at least key absorption peaks from the IR, because those are going to tell you fundamentally what functional groups you have, especially an aromatic ring that is a benzene ring, a CC double bond, or carbonyl group. Now, the NMR spectrum has a number of signals. What you want to do is to examine the signals in the NMR spectrum. First, figure out the number of sets of equivalent hydrogens present. That's going to be related to the number of signals. Secondly, you want to figure out the number of hydrogens present in each set from the peak integration values. That's the information from a spectrum, which is the relative area of those signals. That will tell you the relative number of hydrogens in each signal. Next, you can use the splitting information from the spectrum to figure out the pattern of connection of the carbons, to figure out what carbon is bonded to what carbon. Now, we're going to put all this data together. The next step is to, on paper, draw different possible structures that are consistent with the data at that point, and then stand back and decide which of those drawn structures is the best match with the observed NMR spectrum. In other words, you're going to take each structure and sketch what the NMR spectrum of that would be and make a comparison with that predicted, or rather drawn structure with the actual NMR spectrum. At this stage, you're going to make full use of the chemical shift values for the hydrogens, and those values are provided in tables. There are some tables in PowerPoint slides that were recently posted on Moodle. You can also find information, that kind of information, in your textbook and so forth. All right, let's look at an example. Example number 1. All right, our unknown is called compound X. Very first thing we're going to do is, well, look and see if the molecular formula is given, and it is C4H8O2. As well, it contains a carbonyl group, and that's determined by its IR spectrum. Notice they're not giving us the actual wave number values, but they're just telling us straight away it's got a carbonyl group. First, we're going to compute the HDI, and that's the starting point for that is the molecular formula. Right, the molecular formula, C4H8O2. The first step is to drop all of the non-carbon elements. Just delete the oxygens. It's going to leave you with the formula of a hydrocarbon. For oxygen, that's the most basic and the simplest. We're going to compute the HDI for this now generated hydrocarbon formula. The HDI for that hydrocarbon formula will be the same as the HDI for our actual compound. All right. What you want to do now is, based on that formula CnH2n plus 2, here n equals 4, write the corresponding formula, and that comes out to C4H10. That is, n equals 2, 2 times 4 is 8, plus 2 is 10. Now we're going to compare the number of hydrogens in that formula with the actual number of hydrogens in our equivalent hydrocarbon formula. And we're going to take and subtract the number in our hydrocarbon formula, 8, from the number in that other formula, 10. 10 minus 8 is 2. We divide that number by 2, and that's the HDI value, which is 1. An HDI 1 means that our compound either has a pi bond or a ring. But remember now, we're told it has a CO double bond. That comprises 1 pi bond. In other words, we know that our unknown, X, you know it has a carbonyl group, we know it has only 1 pi bond. That would tell us that the only pi bond is a C double bond O, therefore there are no other pi bonds, no double bonds, no triple bonds, and there are no rings. The next thing we want to do is to find the number of sets of equivalent hydrogens in our unknown. And here's an important rule. The number of sets of equivalent hydrogens in the molecule will equal the number of gross signals in the spectrum, and that's not counting peak splitting. So let's go back to our spectrum. How many gross signals are there? There's 1, 2, 3, A, B, C. That means that within the molecule there are 3 sets of equivalent hydrogens. All right. Now looking at the peak integration information, peak integration gives the relative areas of the signals. For A, B, C, the peak areas are 3 to 2 to 3. Now let's add up those values, see what we get. 3 plus 2 plus 3 gives 8. Well, that's good news, because the total number of hydrogens is 8. This means that in that molecule, it consists of a group of 3 hydrogens, a group of 2 hydrogens, and a group of 3 hydrogens. Most likely, going from A to B to C, well, this. Anytime you have a group of 3 hydrogens, it's doubtless going to be a methyl group. If you have a group of 2 hydrogens, it's likely to be a methylene. So our group of 3, signal A, is likely to be a methyl group. Our group of 2 for signal B be a CH2 methylene. And for signal C, that's another methyl group. Now let's look at the splittings of our signals. Signal A is a triplet, signal B is a quartet, and signal C is a singlet. Signal C means that that methyl is by itself. It doesn't have any neighboring hydrogens. On the other hand, signal A is a triplet. This means it has 2 neighboring hydrogens because, remember the n+1 rule, the number of peaklets equals the number of neighbors plus 1. So if it's a triplet, it's got 2 neighboring hydrogens. And that would correspond to a methylene. That means our CH3 for the signal A is bonded to a CH2. A signal B is a quartet, 4 peaklets. Applying the n+1 rule, that means that the number of neighbors it would have would be 1 less than 4, which would be 3. It has 3 neighboring hydrogens. Again, remember that the number of peaklets is 1 more than the number of neighbors. If we've got 4 peaklets, there's going to be 3 neighbors. So our CH2 must be bonded to a CH3. Now we've already discussed this. CH3, the signal C, is off by itself. It's not bonded to any carbons with neighboring hydrogens. The next step in the process is this. Get out some paper and draw possible candidate structures for that unknown X. That's not as daunting a task as it might seem. You'll find that there aren't that many possibilities, but write them down, and what you're going to do is make a sketch of the NMR spectrum for each of those candidate structures that you wrote. And then look for the one that's got the best match with the actual NMR spectrum. That's the process. You're also going to make use of the chemical shift values from those tables. And okay, so here you put all this together. I hope you can see that's not that hard. There are not that many possibilities. You've got to have an ethyl group, you've got to have a methyl, a C double bond O, and an oxygen, where there's not that many places to stick the oxygen. You can't stick it between the CH3 and CH2. You wouldn't have an ethyl group anymore. All right, so this is one possibility. CH3 bonded to the carbonyl group, bonded to the O, then the ethyl group. All right, what else? What other possibility is? Well, this over here, and that's structure number 2. It is an ethyl bonded directly to the carbonyl carbon, and the carbonyl carbon bonded to O, and then CH3. Now, I referred to the tables. I'm not presenting the tables in this video, but if you go back and check the tables on the PowerPoint slides, there are also references made to them in the video. Now, I've sketched the range of delta values for the different groups. These came right from the tables. Okay, like a CH3 bonded to a carbonyl group of an ester, you expect to see a signal in the range 1.9 to 2.2. Methylene directly attached to an oxygen here. I believe this is, the table shows an ester group is 3.7 to 4.1. Then a methyl bonded to a carbon bonded to an oxygen is 1.2 to 1.4. Oh, also this, don't be disturbed if you don't find an exact match between a table entry and the portions of the structure. Just do the best you can. Find the entry which is the closest possible match and go with that. The chemical shift values that you're going to be writing are kind of guesstimates. They don't have to be spot on. Now structure 2, I looked in the table, I found that you have a CH3 attached to an O to a carbonyl group is 3.2 to 3.5. Notice that this CH3 delta versus this one, that's a lot further downfield. That is, it's a larger delta value, and that's because the oxygen is more electron withdrawing than the carbonyl group. So remember that electron withdrawing group pulls away the electron cloud density, and that causes the chemical shift value to get higher. The CH2 attached to the carbonyl group, I found the value 2.3 to 2.7. And the methyl here, I think I found the methyl attached to a C attached to a carbonyl group. I don't know if there was an ester, but I made the best guesstimate. 1.2 to 1.4. All right, now, so which of these two structures is in best agreement with the NMR spectrum of compound X? Well, when you look, you'll see that structure number 2 is closer to the observed NMR spectrum for the unknown. And let's see, the CH3 here, 3.2 to 3.5. Notice it's by itself. That would be a singlet. And let's go back to the spectrum number 1. And here we got 3.6. Okay, and that's pretty close to this. It'll off a little bit here. The CH2, this is going to be a quartet. It's neighbored by 3. Add 1, you get a triplet. That's 2.3 to 2.7. And let's see what it is in the spectrum. That would be signal B, the quartet. And let's see, it's about 2.3. And you see that's pretty close. The CH3 here, 1.2 to 1.4. That's going to be our presumed signal C. I'm sorry, signal A, at triplet, and that's about 1.1, and it's a tad bit off, but it's still pretty close. The agreements you get for structure 2 is far better than for number 1. Therefore, that's our answer, and this indeed is the correct answer, structure number 2. All right, another example, unknown Y. Chemical formula is, or the molecular formula is C10H14. Well, let's first calculate the HDI value. All right, C10H14, using the CnH2n plus 2 formula with 10 carbons, come up with the formula C10H22. All right, you're going to take the number 22 and subtract from it the number of hydrogens in our actual hydrocarbon formula, 14. So that's 22 minus 14. That's 8. Take the 8 divided by 2 and you get 4. Compound Y has an HDI of 4. Now recall, I mean, that's very high number. Typically, if a compound has an HDI of 4 or higher, there's going to be an aromatic ring, most likely a benzene ring. All right, we want to find the number of sets of equivalent hydrogens here. Look at the number of growth signals. There's 2 growth signals, this and this. Now, I have to do a little bit of free interpretation here. We've got a singlet, and we have this. This is actually a multiplet, a complex multiplet. The singlet would comprise one set of equivalent hydrogens. The complex multiplet would be a set of hydrogens that are coupling with each other, not coupling with the singlet hydrogens, but within each other. Now we look at peak integration. That is the area of 5 to 9. Well, the first thing you want to do, add those together. 5 and 9 make 14, the total number of hydrogens. Well, let me mention at this point, if the sum of the peak areas, well, back up. Those should be whole numbers, and sometimes the peak integration values won't be whole numbers. What you're going to do is take the ratio and reduce the ratio to the ratio of the smallest whole numbers. Change the ratio so it's the ratio of the smallest whole numbers. Now, take those values, add them together, see if they equal the total number of hydrogens. If they don't, multiply everything by 2, and then try again. If they still don't, multiply everything by 3. Well, the problem here kind of is made a little easier because we have rounded off peak areas 5 to 9. 9 and 5 indeed make or equal 14. So it means that in the molecule there's a group of hydrogens, 9 in total, and then a second group of hydrogens, 5 in total. All right. Now, one of the things to note now is one of the things we determined was it's likely to have a benzene ring. Well, if you look at the table of chemical shifts, you find that a benzene ring will show a chemical shift signal between 7 and 9. And if you see something between 7 and 9, you can have the aha moment. It's going to be a benzene ring, most likely. There isn't really anything else in that area. So let's check and see. This signal is at 7.3. Indeed, this for sure looks like a benzene ring. All right, and because it's at 7.3. Okay. Now let's consider the peak splittings. This is unsplit, and it's a complex splitting would say that this is the benzene hydrogens splitting themselves. Now that kind of splitting is very complex. In fact, it's called second order splitting. They don't even follow the n plus 1 rule within themselves. We do note that the signal at 1.3 is unsplit. It's a singlet, and that would mean that those hydrogens have no neighboring hydrogens. Well, the value 5 here would mean 5 ring hydrogens. The value 9, the most reasonable interpretation is this. A methyl set comes out to 3 protons. 2 equivalent methyls would be 6. 3 equivalent methyls, a set of 3 equivalent methyls would be 9. So this value 9 is most consistent with 3 equivalent sets of methyl. The fact that there's no splitting means that that set of 3 equivalent methyls have no neighboring hydrogens. All right, so what it looks like we know so far is that there is a benzene ring with 5 hydrogens, and then a set of hydrogens that together are unsplit without neighboring hydrogens. Now, the total number of carbons that are unknown is 10. Remember the formula. C10H14. Let's do a little bit of math here. Benzene ring has 6 carbons in it. Let's subtract those 6 carbons from the total 10, and that gives us 4 carbons. That would mean then that this signal at 1.3 is a alkyl group with a total of 4 carbons. An alkyl group with a total of 4 carbons. The alkyl group with 4 carbons has, we decided before, 3 equivalent methyls. If you put everything together, well, this benzene ring with 5 hydrogens would have just one substituent, and that substituent would be the alkyl group that would have, we figured out, 4 carbons with 3 equivalent methyls. Right, 3 methyls, that's 9 hydrogens, 4 carbons. An alkyl group, that would be C4H9. A C4H9 group that has 3 equivalent hydrogens can only mean one specific butyl group. Can you figure out what that is? Only one possibility. It would be a tertiary butyl group, a T-butyl group. So we figured out now that this signal is due to a tertiary butyl group, and that T-butyl group would be bonded to a benzene ring. Now, what about the chemical shift values? Well, that is, we know that this is the corresponds to benzene ring 7.3. This is about 1.3, 1.4. If you go to the tables and check out the listed chemical shift for methyls, then, well, I got the range 0.8 to 1.2. Ours is 1.3. That's a pretty good match. The observed 1.3 delta, it's certainly reasonable. Going to be a little bit outside this range, a little bit to the left, because that nearby benzene ring is electron withdrawing, and that electron withdrawal is going to lower the electron density and cause the observed chemical shift to increase slightly. So here we go. We have just figured out that unknown Y is this, tertiary butyl benzene. All right, thank you. Bye.